Hey, welcome. Today, we're diving into one of the wildest and frankly, most controversial ideas in all of tech, taking the enormous, power-hungry brain of artificial intelligence and just launching it into space. Yeah, I know, it sounds like something straight out of a sci-fi novel, but this is a race that's already happening right now.
And this whole crazy race is being driven by one really urgent question. As our AI gets smarter and more powerful, its appetite for resources is just exploding. It's growing so fast that our planet might not be able to keep up. So you gotta ask, are we creating a technology that could literally eat our world?
So let's put some real numbers on this. By 2030, which is not that far away, the global energy demand just for AI could hit a mind-blowing 327 gigawatts. That's not just a big number, that is a colossal amount of power. We're talking about enough to potentially cripple entire national energy grids. And it's not just about electricity, it's also about water. See, all those super dense computer clusters need a ton of water to stay cool. The projection? Over 1 billion cubic meters every single year. So you've got this dual strain on our two most critical resources, and it's pushing us right to the edge, to a real breaking point.
And that right there is the heart of the issue, the crisis we're facing here on Earth. This bottomless demand from AI is creating a serious bottleneck. It's like we've hit a physical and environmental wall that our planet's infrastructure just was never designed to handle.
The truth is, the way AI is growing right now just isn't sustainable. The energy demand is off the charts, and the amount of water needed to cool these things is already causing real conflicts in dry parts of the world. Just to give you an idea, a single large data center can guzzle as much water as a small city of 50,000 people. We're slamming right into a physical wall. So, faced with this crisis, some of the biggest players in tech and aerospace are chasing a really radical solution. They're asking, what if we just move the whole problem off-world? Let's take a look at the incredible promise of building our data centers up there in orbit. Okay, so there are 3 huge advantages to going to space. First, you get unlimited 24/7 solar power, way more potent than what we get through our atmosphere. Second, the freezing cold vacuum of space acts like a perfect infinite radiator to cool everything down. And third, you completely get rid of the need for fresh water. On paper, it sounds like a perfect fix, right? But how do you actually build a data center in space? Well, it turns out there's no single answer. Right now, we're seeing 2 completely different ideas about how to do this, each with its own incredible upsides and its own massive risks. So here they are, the 2 competing paths. On one side, you've got Google with Project Suncatcher, which imagines a whole swarm of small, separate satellites. And on the other, there's Starcloud, dreaming of a single, gigantic megastructure. One is all about being flexible and safe. The other is all about power density and speed. Let's dig in. So first up is Google's Project Suncatcher. The best way to think about this is like a server rack floating in space. It's a supercomputer built from a swarm of smaller, modular satellites, all talking to each other with high-speed lasers. They're planning to use a really clever sun-synchronous orbit, which basically keeps them in constant sunlight. 24/7 power, no need for giant, heavy batteries. They're even aiming to launch a prototype in 2027 to see if it works. And then you have Starcloud, which is going in the exact opposite direction. They're not talking about a swarm. They're talking about a single, colossal structure. We're talking about a 5-gigawatt data center that could be 16 square kilometers. That's huge. Their goal is to get the first high-end Nvidia GPU in orbit by 2026. Now, this approach solves the speed of light lag problem by keeping everything packed together. But you can imagine, putting a city-sized object in orbit doesn't just maximize power, it maximizes the risk. Okay, so who is actually going to build and service all this stuff? Well, Jeff Bezos' company, Blue Origin, is trying to be the answer. They're developing something called the Blue Ring platform. And it's not just a space tug. It's designed to be a mobile, in-space cloud computing hub. They want to be the logistical backbone, the space trucking and maintenance crew for this whole new orbital economy. So, we have these incredible, ambitious visions. But now it's time for a reality check. We have to talk about the absolutely brutal engineering challenges that are standing in the way. Because up in space, the laws of physics are, well, they're not very forgiving, and they could stop these projects dead in their tracks. The first monster problem is heat. Here on Earth, we just use fans and water to carry heat away. Easy. But in the vacuum of space, you can't do that. The only way to get rid of heat is radiative cooling.
You literally have to radiate it away as light. And that process is thousands of times less efficient than what we're used to on the ground. It creates this massive thermal bottleneck. And this heat problem leads to some other huge dangers. For example, to get rid of 5 gigawatts of waste heat from that giant megastructure, you might need radiators that are even bigger than the solar panels collecting all the power in the first place. Then you've got cosmic rays zapping the tiny little transistors in modern chips, which can corrupt data and cause failures. And finally, there's just the insane cost of it all. And this brings us to the cold, hard economic reality. One analysis actually calculated that with today's launch costs, the time it would take to pay back the cost of putting a server in orbit could be tens of thousands of years. Yeah, the entire business model basically depends on launch costs dropping by over 90%. But okay, let's say you solve the physics. Let's say you solve the economics. There's one final terrifying risk. And this one doesn't just threaten a project. It could threaten humanity's entire future in space. And that's the threat of the Kessler syndrome. The Kessler syndrome is, simply put, a nightmare scenario. It's a chain reaction. One collision in orbit creates a cloud of deadly shrapnel. That shrapnel then hits other things, creating even more shrapnel, which causes more collisions, and on until low Earth orbit becomes a lethal, impassable minefield for centuries. And to really get a sense of this risk, look at this. A normal satellite is a target about 10 square meters in size. Starcloud's proposed megastructure, it would be a target of 16 million square meters. It's not just a bigger target, it's a completely different level of risk. A failure here wouldn't be an accident, it would be an environmental disaster in orbit. And that's really the ultimate stake here. Just one mistake, one single catastrophic failure with a structure of this scale could slam the door shut on our ability to use low Earth orbit. It could trap us on this planet for hundreds of years. The consequences are truly generational. Which leaves us with a really tough question. We have a real resource crisis down here, driven by the very technology we're creating. The solution might be out there, in the stars, offering clean energy and incredible potential. But the price of getting it wrong is just unimaginably high. So, to solve our problems on Earth, how much are we willing to risk for our future in space?